All right, let's look at the final modifications to the information retrieval example I've been doing in mumps. First of all, I made a script file in Bash to run the separate programs rather than typing them in individually. It makes for easier overall working with the files. It is called run.script. You don't have to call it .script, but I just do that because it's easier to spot them in a directory. Anyway, what it's got here, the first line tells it to run the Bash interpreter. #bang at the beginning of a line tells Linux that the rest of the line is the name of an interpreter to run. Docs is a Bash variable in this case, and it will be the total number of documents to read. In this case, 15,000 is far too high. Turns out the collection I have is about 9,500 documents, so 15,000 is way too many. But that's fine, I want to read them all. If I want to read fewer than the entire collection, like 2,000 or 5,000, obviously things run faster there, I would set this to 5,000 or something. Anyway, the next thing is I remove the old copies of the database. There is no sense keeping them around from previous runs. We start off with a clean database, it works quicker. Echo is the Bash print command, basically, and it will write out on the screen telling me which step is being run at this point in time. Docterm is pretty much as before. It writes out the document term matrix, creates the document term matrix. $docs is passed to it as a parameter. So I don't have to go into the program and change it every time. It's passed in as a command line parameter. The $ in front of docs tells Bash to translate docs into its value. So it will become 15,000. That's what's being passed. The $ is part of the curious Bash syntax. Anyway, the next one is the dictionary step, and actually broken it down into two parts. dict1.mumps writes out the count and the words as before, but writes them all out and we sort them. So we get a file called wordfreak, which will have all the words in it and all their frequencies. Then I have a different one down here, slightly modified, which is dict.mumps. And it's got two parameters, 5 and 1600, and it writes out word count. Word count is, now we're going to do this automatically. Before I went in there and eyeballed as to where the thresholds would be. The thresholds now are passed as parameters, 5 and 16,000. Words that occur between 5 and 1600 times will be retained. Words that are outside those limits, less than or greater than, won't be. What goes into word count are the words that are outside the range of 5 to 1600. So low frequency and very high frequency. So it turns out in this file, there are some words that are extremely frequent, that are kind of important, like the word IBM. This was the mid-'80s and mid to late '80s, and IBM was hard to write a computer article without using the word IBM. Is it important? Well, in one sense, no, because it's everywhere. But in another sense, yes, because it is the name of a major brand of computers and look-alike computers and so forth at the time. So anyway, IBM is in there. Then there's a file I got off the internet, just looked around for stop lists. These are, it's a file of about, I don't know, maybe 300, maybe less, words that somebody had put together, which are the common words in English, like the and was, and things of that nature, which are not meaningful. There's a lot of those out on the internet. I don't know where I got it in particular, but I do have it. It is stored. It's called stoplist.words, and what I'm doing is I'm concatenating it onto the end of word count. Now, word count is different than wordfreak. Word count only has the words, doesn't have the frequency anymore. Got rid of the frequency. We've got it up here. It's no sense having it down here. It just takes up extra space. What I do is I concatenate these onto the end. Does that hurt anything? What if you got a duplicate? Doesn't make any difference. The way the stop list vector is created, if you get a duplicate, it has no effect. I mean, it just reinstantiates something that's already instantiated. It doesn't change its count or anything. So duplicates don't hurt anything. All right, wordprune.mumps, similar to before, we'll look at. I don't think there are any changes in here. Goes through and removes words that are too high and too low frequency. dt.mumps is creates the inverse document frequency weight for terms, and we get the weights dt.text here. And then finally, weight.mumps goes in there, and this is a new file. I don't think it was in the last time. This goes through the document term matrix and weights the individual terms in each document. Remember, the inverse document frequency weight calculated here is the weight of the term in the collection as a whole. But we want to know what the weight of a term is in a document. Well, to get the weight of the term in a document, we multiply the frequency of occurrence of the word in the document times the weight of the word in the collection as a whole. So if we have some word like IBM, whose overall weight is fairly low, but it occurs in some document a large number of times, its weight within the document will be high. So we are going to convert the document term matrix from counts, the number of times words occurred, into weights. And the weight is the product of the number of times it occurs times the weight of the term in the collection as a whole. So that's basically, and then we can just run this, and I can go in and reset parameters. Now the parameter here is 10. That's the minimum weight. If the weight of a term in a document is less than 10, it gets deleted from the document term matrix. You can play with these parameters quite a bit and get different results. I've already run this actually, but so let's look at the individual programs again. First of all, doc term top mumps here. Here's where it picks up the parameter, the maximum number of documents to read. In my version of mumps, when you enter the program, if there were command line options provided, they will come in as %1, %2, %3. Those are %sign is a valid mumps variable name. Variables that begin with %sign are valid variable names. They're usually used as temporaries, of course, but not as really important variables. But anyway, %1 would be is the first parameter that was passed from the command line. I probably should have said asked if it exists, if $data %1, to make sure somebody passed a parameter, because if they didn't pass it, this would obviously have an error, and that would be put it in here. If not $data %1, we'll probably write a message. Missing parm, something like that. Okay, so if they don't pass a parameter, it'll halt. Since I know the parameter's there, I didn't bother. Anyway, the rest of this I think is pretty much the same. I don't believe there were any major changes. Down here, however, I did make a couple of changes. One of I noticed in looking at the text, I wanted to there were some number of places where it said something or other / something or other else. The slash really should be a blank, because there's two separate words there, joined together with the slash. They really are two separate words. So I initially changed all of the forward slashes into blanks. Let's see. I think there was something else. Yeah, I guess that was it. I don't think there was any others that I actually made it into the final run here. But you can fool around with this translation here to get, because you get the problem of special characters. What are you going to do with them? Oh, there's one I just realized. The hyphen is no longer in this list. Hyphens remain. Hyphenated words were, IBM-PC, something like that. And scrunching them together as IBM PC doesn't make them terribly readable. So I took hyphen out of this list as well. Otherwise, I think everything is pretty much the same. And I'll run out there. Can't run .script. What's next? The next one was dict1.mumps. And dict1.mumps is very simple now. It goes through the dictionary. If you run out of words, sets W initially equal to empty, does a $ order on it. If you run out of words, you halt, we're done. Otherwise, you write out the count. That's the value of the vector. Up arrow dict sub W, indexed by W, is the value, which is the number of times the word occurs in the collection as a whole, a blank, and then the actual word. And as you can see up here, the output of that gets run through the sort, numeric reverse order, and we get word freak. So why don't we look at these before as I'm going on, because they have been run. vi docterm.text. Whoops. Spelled text. Okay, and this is what it looks like, the document term matrix, and you can see there's quite a few lines down at the bottom there. It says 34,902 lines, because we're reading all 9,000 or so of these documents. And what you see there is the document number and the title. Then you see the words with their counts. All right, those are the words that are in each of these. These at signs down here just mean it wouldn't fit on the. That's a continuous line. This this here is a continuous line. It's not. It's not. There's no carriage returns in it. So you. So if it can't print a line, if there's no room for it, it just puts at signs there. That's how VI works. But anyway, that's the document term matrix. The next one up there would have been word freak. And it's a large file. Again, it's got 46,726 lines. Again, VI tells you that when you come in, how many lines you've got and how many characters. And there's the, right at the top, 80,000 times, and for that are with software. Software is way up there. Of course, this is all about these files were all about software. Well, not entirely, but for the most part. Systems. You know, in some collections, of course, the word systems and software would be important words, but, you know, they're not too important in the database, which is largely about software and systems. So, and we see computer is at 5,000 times there, 5,200. Anyway, these are the frequency, and then we get all the way down to the bottom. There's a whole bunch that are one-offs, and they're just numbers for the most part. But they, anyway, next one is word count. This is the one which is slightly different because I took out the frequencies here. These are the ones that are, these are not sorted by frequency. These are just randomly thrown together here. As far as I know, it's pretty much random. And these are the words, these are the stop list words. Let me go into it, say, let's say 10,000. And we're getting some alphabetic, they're actually coming out, I think, alphabetically. Because that's how the vector was scanned. It was for successive words, and that's an alphabetic. Anyway, at the very end here, there's the stop list that I imported from some internet site that I don't remember. And as you can see, it starts there with the A's because you can see the Z's. Zycad, that's actually, it was a name of a product back then. The Zycad was the end of the stop list that came from the dictionary vector, and then this is where the concatenation begins. Okay, next thing there. Next thing is word prune. I don't believe there are any changes to word prune. No, I don't see any here. It basically goes through each of the documents, and if it finds a word inside the stop list, it deletes that instance. So we got up arrow DN is the document number, W is the word. So it found the word in the stop list. If it exists in the stop list, okay, it deletes that instance in the document. At the very beginning here, as you recall, we go through and we read in word count, and we create a vector called up arrow stop.w, and it contains the stop list words. There's nothing stored because all we need to know if they exist. There's no count or anything. So if a word is in word count, it'll be in the vector up arrow stop indexed by a word, and we use that fact down here to find out if it exists. So if W exists in the stop list, that data will come back non-zero, and we delete it from the document term matrix. All right, the next one here is DT. I don't believe there were any changes to dt.mumps. No, there weren't any changes here. Basically, all we do here is we go through, first of all, we go through and count the number of documents. Now, that's what this line does here, is it goes through and successively finds all of the D, and for each of the D, it increments the document count until we run out of Ds. And this is that peculiar, the forever here. 2 blanks after the 4 means do forever. D was already set to empty string. And we get the next value of D. If the next value of D is the empty string, we quit. All right. Notice there's 2 blanks after quit. Quit doesn't take an argument, as they say. So if you want to have something else in the line, it has to be have 2 blanks between where the argument should be in the next item on the line. This is really why postconditionals were put in here, so that you could exit a loop. You can't use an if in here. If D equals empty string, quit. Else, because the rest of the line is gobbled up by the then clause. The else is never executed. When you get to it just doesn't work. So it's just the odd way the if statement worked. It works in mumps, originally worked. So they needed some way of exiting loops without an if. So they came up with the postconditional. So that's basically a mini if there. It tells us that the quit will be executed if D is equal to the empty string. If D is not equal to the empty string, the quit is not executed, 2 blanks, and we'll execute what's left. And that, of course, increments the document count. So anyway, we got a document count. And we go through again for each document D, and then for, let's see, we check to see if the document is empty. Okay? So if $order of up arrow doc sub D and the empty string comes back as the empty string, it means there are no words on this line. In the previous step, we must have deleted them all, in which case we delete the document and we decrement the document count. So basically, we're checking on each document before we work with it, as to whether or not, I don't think the way it's set up now, any documents actually are getting deleted. They might, though. Then we go through, we go through the individual words on the document. In the document, the W starts off as empty string. So long we get the W back. If W is empty string, we quit, and that takes us back up here, and we check it again. We quit the entire loop. It's another way of doing it. Then my system has the word break, which I could have done right here, but I did it more of a standard mumps way. And then I asked the question if up arrow dt of W exists. This is the document frequency. dt is the vector that tells us how many times how many documents each word occurred in. It's different than dict, which is the total number of times a word occurred in the collection. We also want to know, and that's what dt tells us, how many documents the word occurred in. So a word could occur, 1,000 times in the collection, but only in 100 documents. That means it's occurring roughly 10 times per document, of course, on average. Anyway, if dt, if that element of the vector exists, we increment it. That's all. If it doesn't exist, in other words, data was, and notice the 2 blanks after the else, we create it, and of course it has a value of 1. So when we've finished here, we've got this dt vector, which tells us for each word how many documents the word occurred in. Then we go through for every word in dt, we're going through by words here, we calculate the IDF value, the inverse document frequency weight, and that's calculated as the log base 2 of the total number of documents divided by the number of documents this word occurs in. So it's the total number of documents divided by the number of times number of documents this word occurs in, and we take the log base 2 of that. Okay, that gives us a number which is like generally in the range of 1 to 13 or 14, something in that, or it depends upon the size of the collection. But it gives us a number roughly like that. But it gives us an awful lot of trailing digits. And we really don't want an awful lot of trailing digits. I only want 2 digits to the right of the decimal point. That's plenty. This is not that specific a value in terms of weight. The weight is somewhat smudgy. It's not a 7-digit accuracy value. So I use the justify, and the justify results in only 2 digits of to the right of the decimal point. The 1 here simply says is the field length, and if the field length is too small, it ignores it and it uses what it needs. So in most cases, the field length will be a digit dot followed by 2 digits to the right of the decimal point. So on average, it's probably a 4-character field. Some of them get up to double digits before the decimal point, so it could be 5 characters wide. Anyway, the 1 there just simply says use what you want. And I write it out. I write out the inverse document frequency weight. I write out the number of times the word occurs in the collection as a whole, and I write out the number of documents it occurs in, and finally I write out the weight. The reason why I wrote the IDF out first because I want to sort by IDF. Okay, so and that's that one. The next, and that comes out as dt.text. And you can see it was sorted, numeric reverse order, and the output was written to dt.text. I prefer to do in reverse order, get the biggest first and the smallest last. Okay, there you are. The highest value here was 13.51, and there were a lot of words at 13.51. And that the next number is the number of times it occurred in the collection, and the next one is the number. Is that right? Let's go double check here. So we see down here, yes, it's number of times it occurred in the collection as a whole, followed by the number of documents it occurred in. So if we look here at this one occurred, this Versant, it must have been a product name, occurred 9 times in the collection, but it occurred in 1 document. So it's highly clustered. It's a very concentrated term. That's why it has such a high value. And you can see they're all pretty much that way, that of 13.51. They really occur in all the times they occur in 1 document. And okay, then we've got some others that gave us a similar value. Remember, it's we're chopping at 2 digits to the right of the decimal point. So these are really different than one another in the far decimal digits, but we don't care about that. Woolworth is in here. And let's find IBM, for example. IBM PC has a weight of, and there's non-IBM. IBM compatible. IBMs, we should have a plural. That was probably possessive, IBM apostrophe S. I pull apostrophes. So IBM itself is not in here. No, it got knocked out for frequency, I guess. All right, the next thing is weight.mps, weighted.mps. And this is relatively, well, maybe if I spelled it correctly. Let it spell it for me. All right, there it is. And there's the parameter coming down, which is the minimum. I pull it off as a percent sign 1. Again, I should check to see if it exists. I go through for each document. I write out the document with some asterisks to make it stand out. I write out the document number, a blank, and the title. But I don't write the entire title because it tends to run on. Some of them are very long. I only write out the first 70 characters. Extract pulls the characters starting at position 1 out through including 70. If a title is shorter than that, it doesn't hurt. If it's longer than 70, it truncates at 70, basically. So I get a shortened title. And then I go for each word on the line. And a slightly different way of doing the for loop again, but it's before I do the do, I check that there's the quit with the post conditional. It's the 2 blanks here. So 2 blanks after the for as well. If you're not going to have any arguments to the for, you have to have 2 blanks. But anyway, it's going to pull the next word from a document. If the word is empty, this for loop quits, and we go back to the outer for. This line quits, and when the outer for reiterates, and we get a new document number. Otherwise, it invokes the do, and the do invokes this inner block here. And what we do is we set up arrow document number, comma W equal to itself times the inverse document frequency weight for the word. So docs of dn, comma W is the number of times the word W occurs in document dn. We multiply that times the weight. Then we check if it's less than min, which was a parameter, we delete it, and we go back up and get the next word. Otherwise, we write out this is continuous on a line. We write out a blank, the word, and in parentheses, the new value, the weight. Okay. When we get back to the outer loop, we'll write 2 blank lines. So each of these documents is separated from the previous one. Okay, that's what it looks like. So here would be a, let's see if anything, there's telephones. And anyway, here, for example, and now you remember the document numbers are coming out alphabetically, not numerically. In my case, the numbers come out alphabetically, unless they're padded to a certain length or something. Okay, so document 10,000. Oh, I guess we do have more than 10,000. 10,065. I thought it was about 9,600, but I was wrong. ITTC Strong Channel. That was I don't think it exists as a company anymore. International Telephone and Telegraph or something like that. And you can see the words here and their weights. Let's see. ITT is in there, and it's got a very high weight over here. You can see it's 54.6. So that's not. How about Oracle down here? What do we got here? Oracle was a relatively new company, but it does exist. Oracle ended up with a weight of 19.95 in this document. It is the most heavily weighted item in the document. As I'm scanning it there, it's the quarter is the next. That, of course, would be a fiscal quarter. But nonetheless, let's see down here. Let's see. Some of these that you don't even remember, like Watcom was a compiler for the C language back when. And Watcom got a score of 55.9, which means it's very important in this document. Good got in here as a relatively high scoring term. Sometimes you get stuff like that. Nothing you can do about it. It's information. Nobody would search by the way. I don't know. Maybe somebody would search for the word good, but if they did, it would show up. So piracy, pirates, things of that nature. Okay, so that was the modified. That's the modifications, including the weighting script. Now the next thing would be something like retrieval, where you actually have a query, and you go through and you look for documents that contain the word, and then you would weight them. So if you found a whole series of documents, you would, for each document, get a score. So let's say the query had 3 words in it or something like that. You would for each document add up the score for each of those words if the word in fact occurs in a document, and you would get a total for each document, and then you would rank the results. So the documents with the highest score would appear first, and documents with the lowest score would appear last. That's how Google does it, and all the others. They rank them based on a score. The term or terms you used, how frequently those terms occurred, and what the weights of those terms were, and they come up with a score for each document, which is what you get. All right.